Swayam Prabha. Digital India. Educated India.
Okay, so let me go back to what we did in the last class so that it's more clear. We have seen that our equations are in this form, right, where x bar is the vector of state variables, right, 8 state variables, and u is the vector of control parameters. We will keep only 4 basic controls in this vector. Right. So, all the equations put into this compact form. Now, what we are trying to do is we are trying to linearize these equations around an equilibrium flying condition which is a longitudinal trim, right. Trim or equilibrium, sometimes people get confused with this because trim is related to locking your control surfaces, right, isn't it. So, in a general sense people do not like to use trim for equilibrium condition, but for aircraft it is a valid word. And we are denoting our equilibrium condition with the subscript naught. So, u naught is non-zero, other two velocities are 0. Rates are all 0. And it is a longitudinal flying condition. So, the wing bank angle is also 0. Let us say the pitch angle is not 0, so that I am talking about all kind of flying conditions in the longitudinal plane. Now, we want to linearize our equations of motion around this longitudinal equilibrium condition. Okay. Right. And I said that we can introduce perturbation, from this equilibrium condition. So, perturbation can be introduced like this. So, my new variables are these, right. So, aircraft flying in perturbed condition, no, condition which is different from equilibrium flying condition, right, and the perturbations are these perturbations in each variable. Right. So, in general I can write this x bar as sum of this equilibrium condition plus the variation in x from the equilibrium condition. Similarly, I can also write for u the new condition right perturbed condition. Now, let us try to substitute those variables in this equation 1. Right. Now, let us expand this function using Taylor series expansion. Right, higher order terms which will have square or cubic of this perturbation variable, right. I am assuming that the perturbations are small, right. In that case we can drop these terms, right. So, what you have is this equal to this after we drop this, right, and we assume that when we drop this we assume that So, looking at only a small motion about the equilibrium condition. Now, this is equal to this identically, right, or even otherwise, because we are talking about this as the equilibrium condition, this function is going to be 0, isn't it? So, when we are talking about equilibrium condition or the steady state of the aircraft, what it means is right, change in time rate of change of variable is going to be 0, that is what defines the steady state, right. So, this is going to be 0, right. So, automatically you are solving this equal to 0 for the equilibrium conditions. And also, no, think about any condition, not just the equilibrium condition. This is true, right, this is in general true. So, this is also true. In the last class I directly did it. I am trying to explain how we get to this, right. So, we can set, no, this is equal to this, or even otherwise if you talk about steady state, this is 0 and this is 0, right. The difference here is that you may be flying any condition, let us say you are not flying an equilibrium condition, but maybe a maneuver, right, where you still want to look at the perturbed motion of the aircraft, right. There this formulation is useful, because you are not dropping these two, because you are at equilibrium states, right, where this has to be equal to 0 and this also has to be equal to 0, but also for the region that this is equal to this, right. So, this is what you can use for linearizing your equations of motion, and we already finished linearizing the force equation and one moment equation. I am going to write down the final form of the linearized equation. All right. Second equation is the equation, the force equation in the y direction, right. In general, these forces are going to be function of all the variables, right, but we are trying to retain only those derivatives which are important. Okay. So, this derivative you see is the change in the force in the normal direction with respect to the pitch rate, right. M is the pitching moment. This derivative is rate of change of pitching moment with respect to the pitch rate, defined like this. Okay. So, you can write in general these derivatives in this form. Okay. rate of change of rolling moment with respect to the variable, right. This is how you will define it. So, I have been using L prime for rolling moment. I will keep this to distinguish it from left. Remember to simulate the accurate motion of aircraft. If my wind tunnel measurements, okay, gives me this as I am measuring this, and this is a not a small value, then I have to include that, right, in the equations of motion. So, whatever data comes to you from the wind tunnel measurements, you have to keep it as it is, and then you have to write down the equations of motion accordingly, whether it is perturbed equations or the full form of equation. So, you have to write your equations of motion in such a fashion that you can include all the data that is provided to you, right, and this data is coming from experiments. So, somebody is no somebody doing experimental measurements is going to give you the aerodynamic database, right, which will have all these derivatives or all the forces as functions of all variables, right, whatever we can measure, and then you need to model them, right, because you want to study the motion of aircraft using the data given, right, and that is not our job, okay. That part is someone else is doing that job, right, someone else is collecting the data, he is giving you the data, and he is asking you to look at the aircraft or simulate aircraft equations, aircraft behavior, right, using the database given to you. So, if I want to simulate the perturbed behavior, then I have to use these perturbed equations, right. In general, if you want to look at the aircraft behavior, no, trying to figure out the trajectory or something like that, then you have to use the original form of equation, right. Linearized form of equations are normally used for looking at the dynamic stability properties of aircraft. Okay, so we already have 6 equations linearized, we have 2 more equations or less, yeah. So, alright. So this is equal to this from this equation, right. So I can cancel these out, and let us look at what is left. Right, and now use this reference flight condition and see what is left. So phi naught is zeros, cos phi naught is 1, this is 0, so what is left is yeah, but this R naught is 0, right. Now you can repeat this exercise and you will find that delta phi dot is equal to delta p. So we have linearized all our equations around this particular flying condition. Okay. So if you have any other flying condition, you have to repeat this exercise, right, because here what we have assumed is that alpha naught is 0, right, but alpha naught may not be 0 in longitudinal flight. Okay. Now let us start looking at some of these derivatives. See, what we are interested in finding out is we want to find out how the dynamics of aircraft is getting affected because of the change in aerodynamic forces, right. So because we get some idea about how we are going to, let us design our aircraft so that we can control these derivatives, isn't it. So first thing is we should know what these derivatives are. So we will start looking at them separately, not really looking at all of them, but some of them, okay, and then you will know how to find others. Okay. We will first try to write down what this force x is, okay, and afterwards we are going to find the derivatives by taking the derivative. So I will only write down the forces. Okay. So, x is the sum of all the forces, including the thrust. If you think that the thrust is also going to change with respect to the variables of the aircraft, then you have to include that also, right. So, here we will try to keep that. Okay. If the thrust is not changing with the perturbation in forward velocity, then we can drop that, right. So, aircraft is actually climbing, right. So, if I say that the thrust is acting along the body fixed x axis, then this force x is T plus a component of left is going to act towards the body fixed x axis, right. I want to find out this derivative xu, right, which is right. Remember, I already said that these derivatives have to be evaluated at the equilibrium flight condition, right. So, I am going to evaluate this at equilibrium flying condition, which is given as this. Here alpha naught is 0 because of this, W naught is 0. So, alpha naught is 0, yeah. Yeah, so you can generally also you can find this derivative and right, you can write the general form and then keep on evaluating this derivative at different equilibrium conditions, right. Is that what you are saying? Okay, what you are saying is you are okay, alpha naught, all right. So, you get only expanded form. Now you have to remember one thing. Now we are talking about pre-stall regime of flight, right. In general, if you are talking about all kind of flight regimes where you are also trying to go into post-stall regimes, then these derivatives can become nonlinear functions of the variable itself, but here they are going to be constant, right. And also in the pre-stall regime, when alpha is roughly about 15 to 20 degrees, right, from 0 to 15 let us say, or maybe a little more than that, you can make assumptions like sin alpha is equal to alpha, isn't it. So when we are talking about pre-stall flight regimes, it gets much simplified, it is not complicated, and these derivatives are going to be constants. Okay. So XU, let us also try to expand these terms. Left is equal to half rho v square s into CL, right. Here both CL and V are functions of u, right. V squared is right. Similarly, I can write the derivative of the drag with respect to u is this right, and what is this derivative, right. What is alpha? So I am talking about small angles, so I can no, take this approximation, right. So what you have is this, okay. Now as I said, we have to evaluate the derivative at the equilibrium flying condition, right, and actually that is how you are going to keep your model in the wind tunnel, isn't it. You are not going to give a motion to the model, you are just keeping the model static model in the wind tunnel, and you are trying to measure the forces and moments. right. Okay, so now I am going to look at my reference flying condition and try to simplify this. This subscript is referring to the so you can see this complete form, right. So what we will do is we will assume that alpha naught is 0, okay. So that is one such condition. If you want you can retain it in this form, okay. I am only trying to give you an idea of what this force is with respect to change in velocity, forward speed. Okay, if you want you can retain these terms like sin alpha naught, cos alpha naught and so on. Okay, so let us try to so my V naught squared is E naught squared, right, because other two terms are 0. We have second or third term which is having the derivative of this, and if I want to evaluate it at the equilibrium flying condition, because of this term here it will be 0, right. So I am going to write 0 for that, and right. This term is again 0, right, because look at this derivative. So if I evaluate this derivative at the flying condition when W naught is 0, then this becomes 0. So the last term there is also 0. Now if I say this alpha naught is 0, if you want you can keep it, okay, right. If you want you can keep it for non-zero alpha flying condition, right. Okay, let me not rewrite this. What I want to point out here is the CL is a function of this forward speed, right, and this term is going to be significant when whenever we have to think about the compressible flows, right, or at higher speeds. The subsonic, at subsonic speeds there is going to be very small or 0 probably, right, but at higher speeds this is not going to be a small term. In that case you have to include this also in your model or the equations of motion. So let me quickly tell you what this derivative is when your flying condition is this, right, that is what we are having here. Okay, you can check this, and here I have assumed that there is no change in thrust with respect to the forward speed. Okay, so we can stop for today.